In this lecture, we will study about scattering theory. We will come to know about scattering of light. So, what is scattering of light? Scattering is a general physical process whereby some form of radiation, such as light or moving particles, for example, are forced to deviate from a straight trajectory by one or more localized non-uniformities in medium through which it passes. A large number of molecules are present in Earth's atmosphere. These molecules scatter light in various directions. The air is composed of many tiny particles, including dust and water vapor. As the sunlight passes through the air, the shorter blue light waves are reflected and refracted by the particles, while the other colored light waves, being longer, are unaffected and are not reflected by the water vapor or dust in the air. So next in this slide we will study the next phenomena of scattering. When light passes through a substance or gas, a part of it is absorbed and the rest scattered away. The basic process in scattering is absorption of light by the molecules followed by the re-radiation in different directions. The strength of scattering can be measured by the loss of energy in light beam as it passes through the medium. In absorption, the light energy is converted into internal energy of the medium, and in scattering, the light energy is radiated in other directions. So the strength of scattering depends on size of particle causing the scattering and the wavelength of light. The scattering is proportional to 1 over h4. So this is known as Rayleigh law of scattering. So the red light is scattered the least and violet is scattered the most. This explains why red signals are used to indicate danger. Because red light is scattered the least. So there is a question why the sky looks like in blue color. The blue color of sky is due to Rayleigh scattering. As light moves through the atmosphere, most of the longer wavelengths pass straight through. Little of red, orange and yellow light is affected by the air. However, much of the shorter wavelength light is absorbed by the gas molecules, and the absorbed blue light is then radiated in different directions. It means it gets scattered all around the sky. Whichever direction we look, some of this scattered blue light reaches to us. Since we see the blue light from everywhere overhead, so that's why the sky looks blue. So the next is why clouds appear white. So clouds appear white because the light coming from the sun has to pass through the water droplets and ice crystals, or we can say that seven color of visible spectrum, that is red, orange, yellow, green, blue, indigo, violet, which when combines form white light, and this process of combining is done by water droplet or ice crystal present in the clouds. On the whole, we can say that light is reflected in many ways which combine to give white color. in this slide, basics of scattering. From word scattering, one thing comes into mind is that it is the phenomena of light. So when there is dense medium, some part of light is absorbed and some is reflected, and reflection is either regular or irregular. But here we study the particular type of reflection done by a very small spherical particle. Reflection, transmission, these all are unidirectional, but scattering is not unidirectional but occurs in different ways and at different angles. So almost everything we know about nuclear and atomic physics has been discovered by scattering experiments. Like Rutherford discovery of nucleus, the discovery of subatomic particles such as quarks. Almost all discoveries has been discovered by scattering. So in low energy physics, scattering phenomena provide the standard tool to explore solid state system. Example, neutron, electron, X-ray scattering, etc. As a general topic, it therefore remains central to any advanced course on quantum mechanics. In these lectures, we will focus on general methodology, leaving application to subsequent courses. So further about light scattering. So light scattering is a form of scattering in which light in the form of propagating energy is scattered. Light scattering can be thought of as the deflection of a ray from a straight path, for example, by irregularities in propagation medium, particles, or in interface between two media. Deviation from the law of reflection due to irregularities on the surface are also usually considered to be a form of scattering. So when these irregularities are considered to be random and dense enough that their individual effects average out. So this kind of scattered reflection is commonly referred to as diffuse reflection. So most objects that one sees are visible due to light scattering from their surface. Indeed, this is our primary mechanism of physical observation. Scattering of light depends on the wavelength or frequency of light being scattered. So these are the simple type of scattering. Like scattering may be elastic or inelastic and quasi-elastic scattering. So elastic scattering when the wavelength frequency of the scattered light is same as the incident light. So this happens in Rayleigh scattering and Mie scattering. And inelastic scattering is the emitted radiation has the wavelength different from that of incident radiation. So this happens in the Raman scattering fluorescence. So quasi-elastic scattering is the wavelength frequency of scattered light shift, for example in moving matter due to Doppler effects. So there are some kinds of scattering in which scattering can occur, like Raman scattering, Rayleigh scattering, Brillouin scattering, Tyndall scattering. So from figure we can see that all light scattered when sunlight falls on atmospheric particles, they are scattered in different directions. So from figure we can see that the phenomena of scattering clearly. So first we will explain Tyndall scattering. The scattering of light by particles in its path is called Tyndall effect. So when a beam of sunlight enters a dusty room through a window, then its path becomes visible to us. This is because the tiny dust particles present in the room scatter the beam of light all around the room. When this scattered light enters our eyes, we can see the beam of light. Tyndall effect can also be observed when sunlight passes through the canopy of a dense forest. Here, tiny water droplets in mist scatter sunlight. So, in 1859, Tyndall discovered that when white light, consisting of seven colors, is passed through a clear liquid, is passed through a clear liquid having small suspended particles in it, then the blue color of white light having shorter wavelength is scattered much more than red color having longer wavelength. So the blue light has longer wavelength, so it is scattered more easily. On the other hand, red light has shorter wavelength, so it is not scattered much. So the next is Rayleigh scattering. Rayleigh is elastic scattering from small particles such as atoms or molecules, resulting in scattered radiation that occurs in all directions uniformly. So Rayleigh scattering is wavelength dependent. So with shorter wavelength, the more scattering. So the next type of scattering is Raman scattering. Raman is an inelastic scattering mechanism where the frequency of scattered radiation is changed by the gain or loss of energy, which correspond to energy levels in an atom or molecule. So this is called Raman scattering. So the last one is Brillouin scattering. The scattering of light from acoustic modes is called Brillouin scattering. Brillouin scattering is an inelastic scattering mechanism which typically occur in light scattering from solid materials. The incident radiation wavelength is modified by the energy levels of sound waves or phonons in the solid material, which is typically very small shifts. So the color of scattered light depends on the size of scattering particles. So dust particles and water droplets suspended in atmosphere are much larger than the wavelength range of visible light. When white light coming from the sun hits these larger particles, it gets reflected or scattered in different directions. Due to this, scattered light appears white. Thus, when white sunlight falls on larger particles present in atmosphere, it is scattered as such, so the scattered light also appears white. The air molecules present in atmosphere are smaller than the wavelength range of visible light. So when light coming from sun hits these very small air molecules, it behaves differently. Since different colors of white light have different wavelengths, so they are affected differently. The lower wavelength lights like blue are scattered much more by the air molecules, but the higher wavelength lights like red color are scattered much less. Thus, when sunlight falls on extremely small particles like air molecules, it is not scattered as white light. The molecules of air scatter mainly the lower wavelength of light, which have blue shades. So as in previous slide, we have a question why clouds are look like blue or white. So there is a question why sun appears red at sunrise and sunset. The sun and surrounding sky appears red at sunrise and at sunset because at that time sunlight has to travel the greatest distance through the atmosphere to reach to us. So during this long journey, most of blue color present in sunlight has been scattered out and away from our line of sight. So the light reaching us directly from rising sun or setting sun consists mainly of longer wavelength red color due to which sun and surrounding sky appears red. But when sun is overhead in sky at noon, the light coming from it has to travel a relatively shorter distance through atmosphere to reach us. So during this short journey, only a little of the blue color of white light is scattered. Since the light coming from overhead sun has almost all its component colors in the right proportion, it appears white to us. Now, what is the significance of scattering in quantum mechanics? The study of nature or other theories in classical is mostly based on scattering. More precise observations are obtained through scattering rather than any other studies. Because in scattering we study the interaction of particles. Observed calculations or data were obtained after the direct interaction with particles so that will be more reliable. So also so important in quantum mechanics because in quantum we deal with quanta, small or tiny particles. So for their absolute result, we need scattering also in quantum mechanics. So scattering of one object from another is perhaps our best way of observing and learning about the microscopic world. Indeed, it is the scattering of light from objects and subsequent detection of the scattered light with our eyes that give us the best information about the macroscopic world. We can learn the shape of objects as well as some color properties simply by observing scattered light. There is a limit to what we can learn with visible light. In quantum mechanics, we know that we can't discern detail of microscopic system like atoms that are smaller than the wavelength of particle we are scattering. Since the minimum wavelength of visible light is about 0.25 microns, so we can't see atoms or anything smaller even with the use of optical microscope. So the physics of atom, nuclei, subatomic particles and the fundamental particles and interaction in nature must be studied by scattering particles of higher energy than photons of visible light. Now, what will more about scattering? Scattering is also something that we are familiar with from our everyday experience. For example, billiard balls scatter from each other in a predictable way. We can fairly easily calculate how billiard ball would scatter if the collision were elastic but with some energy loss and the possibility of transfer of energy to spin, the calculation becomes more difficult. So what is the scattering phenomena and background? In an idealized scattering experiment, a sharp beam of particle A of definite momentum k are scattered from localized target B. So as a result of collision, several outcomes are possible. When a sharp beam of particles are scattered from localized target, that is B, then A plus B will be elastic, or A plus B inelastic, A plus B plus C is also inelastic, and then C is absorption. So these are three outcomes are possible as a result of collision. So in a high energy and nuclear physics, we are usually interested in deep inelastic processes. So to keep our discussion simple, we will focus on elastic processes in which both the energy and the particle number are conserved, although many of the concepts that we will develop are general. So first we have differential cross-section in scattering phenomena. Both classical and quantum mechanical scattering phenomena are characterized by scattering cross-section sigma. So first consider a collision experiment in which a detector measures the number of particles per unit time, that is capital N d omega, scattered into an element of solid angle d omega or d in direction theta phi. So this equation can be explained in the next lecture from diagram. So this number is proportional to incident flux of particle, that is Ji, which is defined as the number of particles per unit time crossing a unit area normal to the direction of incidence. Then collisions are characterized by the differential cross-section defined as the ratio of number of particles scattered into direction theta or phi per unit time per unit solid angle divided by incident flux. So d sigma over d angle, solid angle, is equal to n over Ji. And from differential, we can obtain the total cross section by integrating overall the solid angle. Then we will obtain total cross section, that is sigma is equal to integral d sigma over solid angle into d omega is equal to integral 0 to pi d phi 0 to integral 0 to pi d theta. These are the limits of phi and theta. Phi is from 0 to 2 pi and theta is from 0 to pi. Sin theta d sigma over d omega. The cross section, which typically depends sensitively on energy of incoming particle, has dimension of area and can be separated into the sigma elastic, sigma inelastic, sigma absorption and sigma total. So in the following we will focus on the elastic scattering, where the internal energy remains constant and no further particles are created or annihilated. For example, low energy scattering of neutrons from protons. So before turning over to quantum scattering, let's consider the classical scattering theory. So let's consider the classical theory in scattering phenomena. In classical mechanics, For a central potential V of r, the angle of scattering is determined by the impact parameter, that is B of theta. The number of particles scattered per unit time between theta and theta plus d theta is equal to the number incident particles per unit time between B and B plus dB. So therefore, for incident flux Ji, the number of particles scattered into solid angle d omega is equal to 2 pi sine theta d theta per unit time is given by n d omega is equal to 2 pi sine theta d theta n is equal to 2 pi b dBji. So as we know that d sigma of theta over d omega is equal to n over ji, that will be equal to b over sine theta mod of dB over d theta. This will be obtained from above equation by simplifying n over ji is equal to b over sine theta into dB over d theta. So this is the equation we have obtained from simplifying in the previous slide. D sigma of theta over d omega is equal to b sine theta of dB over d theta. So for elastic scattering from a hard impenetrable sphere that is shown in figure, we will get b of theta is equal to r sine alpha, that is r equal to r sine alpha is equal to pi minus theta over 2, and we will get minus r cos theta over 2. So as a result, we find that dB over d theta is equal to r over 2 sine theta over 2, and then the sigma of theta over d omega is equal to r square over 4. So as expected, total scattering cross section is just integral d omega d sigma over d omega is equal to pi r square as the projected area of the sphere. So now from classical Coulomb scattering, V of r is equal to k of r. Particle follows hyperbolic trajectory. In this case, a straightforward calculation obtained the Rutherford formula, that is d sigma over d omega is equal to b sine theta into dB over d theta is equal to k square over 16 e square into 1 over sine 4 theta by 2. So this is the Rutherford formula. Now basics and notations in quantum scattering. The simplest scattering experiment, the plane wave implying on localized potential V of r, the electron striking atom or alpha particle.
Class, in previous lecture we have discussed about the basics of scattering and what does scattering mean,
basic
then
setup,
why we need the
flux of
scattering in
particle,
quantum mechanics.
All
We have
at same
short
energy,
view about the scattering and the
scattered
quantum
from the
scattering,
target
but in
and
this
collected
lecture
by
we
the
will
detector,
put
which measure
brief
the
note
angle
on
of
the quantum
reflection.
scattering.
So this is
So what the basically quantum scattering is, for the quantum scattering or the basics of quantum scattering, we need to solve the time dependent Schrodinger equation, for which we need to consider the wave packets.
A small cross section d sigma.
I would remind why we
and
need
then the target is the small atom. In the principle, if all incoming particles represented by wave packet, the task is to solve then time-dependent Schrodinger equation, that is iota h cut curly t psi of r t is equal to minus h cut square over 2m del square plus v of r with wave function phi psi of rt, and we will find the probability amplitude for the outgoing waves. So we will discuss in the next slide. And now we will consider a wave of vector k.
Class here we represented the plane wave, which
then
is more
we can see
medium,
that
and
plane wave and scattered wave from the figure. So the wave function is a combination of two waves. First one is plane wave and second one is spherical wave. So for this, wave function will be equal to AE IK naught dot R, where A is the amplitude and E iota K naught dot R is the equation for plane wave, plus A F theta phi E I K dot R over R. This is the equation for spherical wave. From figure we can see that we have a plane wave and a spherical wave. So the wave function will be a combination of these two waves. So from this figure we can now the plane wave is a So from this figure we can clearly understand the quantum theory of scattering. Like we have an incident particle of mass m and a target. So when incident particles hit on the target, the way incident particles may scatter with scattering angle theta, and the amplitude of the incident particles are a, and the equation of the scattering waves is E iota k r, and the equation of the incident particles is E iota k. Now the plane wave is always incident along z direction. So in quantum theory, if iota kz is a plane incident wave which encounter the potential v of r produces outgoing spherical wave. So we can see that from figure we have a plane wave, and this plane wave incident along z direction, and in quantum theory iota kz is a plane incident wave which encounters the potential v of r and produces the outgoing spherical wave. Now we have to find the scattering amplitude of the wave function for the scattering wave is psi of r is equal to, for plane wave E iota kr plus for spherical wave f of theta E iota kr over r. So where f of theta is equal to summation L is equal to 0 to r infinity into 2L plus 1 FL into k PL cos theta, and where FL into k is equal to SL of k minus 1 over 2 iota k. So FL of k is defined by the phase shift SLK, and where SLK is equal to E2 iota SL of k. So after substituting these values, we will get
Here equation 1 represents the total amplitude of the wave where you had divided it into the two parts, the plane wave and the scattered wave. The plane wave, as you know, the amplitude of the plane wave is the E bar iota kr, and this.
In this slide, we simply take the formula of scattering cross section and in this formula we simply put the values of psi and psi steric, and after putting the values of psi and psi steric we will get minus iota h cut over m real of E minus iota kr plus f of theta steric E minus. We apply steric on this equation E minus iota k of r over r, and then del multiplies with E iota kr plus f of theta E iota kr over r, and then we will simplify minus iota h cut over m real of E minus iota kr plus f steric of theta E minus iota kr over r into iota k E minus E iota kr plus f of theta iota k E iota kr over r plus f of theta E iota kr, and then del of 1 over r. Simply we apply del operator on E iota kr and then f of theta E iota kr over r, and after applying the del operator on these two terms we will get f of theta iota k E iota kr over r plus f of theta E iota kr, and then del on 1 over r. Now in the previous slide, after putting the values of psi and psi steric, we simply apply del operator on the two terms, and then we will get minus iota h cut over m real of iota k E minus iota kr into E iota k plus k I of f of theta square E iota k r into E minus iota kr over r square plus so on. So the scattering cross section is equal to minus iota h cut over m into iota k minus iota h cut over m iota k of f of theta whole square over r square plus so on. And then after taking minus iota k common from these terms, we will get j is equal to h cut k over m plus h cut k over m or f of theta whole square over r square plus so on. So we will neglect the higher order terms, and after neglecting we will get scattering cross section j is equal to h cut k over m plus h cut k over m or into f of theta whole square over r square with e of r unit vector. So now as we know that area is equal to A is equal to r d theta, and for small patch d A is equal to dr into dr d sigma d omega. Since r is not changing, so the AD area will be dA is equal to r square d omega. The flux of particles at subtends angle d omega is and d omega is equal to j of E into E of r dA, and after putting the value of j h k over m plus h cut k over m E r unit vector f of theta whole square over r square into E r unit vector dA, we will get after simplifying h cut k over m f of theta whole square over r square d omega, which is solid angle. So this is the scattering cross section.
So from all of the previous calculations, I have mentioned all the numbers for the equations
and d omega over ji, and then n d omega is equal to j dot t unit vector dA over ji, and here we will take d sigma is equal to, after putting value of j, h cut k over m, f of theta whole square over r square, with r square d omega over ji is equal to h cut k over m, and then we will get d sigma is equal to f of theta whole square d sigma. So from this we will get the relation d sigma over d omega is equal to f of theta whole square. So this is a cross section